So we are moving on to the day 4 session 2. So the session will be handled by Dr. Venugopal sir, who is a former professor from the Presidency University, Bangalore. So let me invite Mr. Ebin Paul for introducing the speaker.
Hello, am I audible? Hello.
Yeah.
So a warm good morning to all of you. Today we are having a section on data analytics for Industry 4.0, which is taken by Dr. Venugopal Kanavalil sir. He's a professor at Computer Science at Presidency University, Bangalore. He has got his doctorate in Computer Science and MTech in Electricals from IISc Bangalore. He has got his bachelor's in Electrical Engineering from NIT Calicut. He has been associated with the information technology sector for the past 26 years, working on industry solutions for retail, telecom, banking and financial services, and energy utilities business domains for domestic and international customers. He has previously served as group manager at IBM, the Cognitive Business Division of Global Business Services, BU. He has also held senior roles at reputed IT companies such as SP, Toshiba Software, and Wipro Technologies. So on behalf of Mechanical Engineering Department of Vishwajyoti College of Engineering and each one of us present here, I invite Dr. Venugopal sir for the section. Sir, please.
Thank you. Hello, everyone. I hope all of you can hear me.
Yes, sir, it is clear.
It's clear. Okay, so I actually, let me start with a small disclaimer. I don't have PPT, PowerPoint software. So what I've done is I've created a PDF. So I'll be navigating through a PDF. So the navigation may not be as seamless as in a PPT, but nevertheless, I hope you will bear with me. Okay, so let's start off. Actually, Abhin has already given an introduction. I actually had a slide. I'm not getting control. What's that? Yeah, so let us start with the agenda I have for this presentation is like as follows. I have an introduction and which is something about myself. Eben has to some extent already covered that, but I'll nevertheless step through that. So what I plan to do is that I'll actually give some background information on Industry 4.0. And especially you'll be here about things like smart factory concept. So that is something I'll pay a little bit of attention to. And then I will actually, since the major part of it is to deal with analytics, we'll also, since analytics is going to be one of the main drivers, or rather one of the compelling drivers for Industry 4.0 and one of the consequences thereof, I'll be talking about big data and parts of it, relevance of big data analytics. And I will also take some classical use. There are many things, many opportunities are barely scratched the surface, but there are already some very fairly relevant use cases available, like preventive and predictive data maintenance, which is typically used in manufacturing. So I'll cover some parts of it, and then I'll also talk about something related to challenges or opportunities of Industry 4.0. So this will be the basic flow of the presentation. So let me start off without further ado. So yeah, Eben has already covered, but I'll just for the sake of showing it, it's there. So I've got a doctorate in computer science and a master's in electrical engineering from IISc Bangalore. And prior to that, a bachelor's in electrical from NIT Calicut. And those days it was used to be called REC Calicut. Now it's called NIT. And I've been, ever since that, I've been in industry close to about 26 years or so. I've worked in industry in various companies, most recently being at IBM at Bangalore. And their Embassy Golf Links, that's where we had our park, and my office used to be located there. And this is related to that Watson. You must have heard about Watson Cognitive Platform. So we were basically the GBS, Global Business Services Unit, which is actually looking at solutions centered on Watson. So prior to that, I've worked on companies like Hewlett-Packard. Now it's called Hewlett-Packard Enterprise, again based out of Bangalore. Toshiba Software, again based in Bangalore. Wipro, on and off in Cochin, they have a software, a unit, SEZ here, as well as Bangalore and other geographies. So totally, as I said, a different kind of profile where I had about 26 plus years in industry. And after that, I've come into academics. So most recently, I was working in Presidency University. And the reason I'm here in Kerala is that because of this COVID thing, a lot of shutdowns and things like that, I've kind of relocated to Cochin. So that's it. Let me proceed to the topic. So here, Now, all of you may have heard about Industry 4.0, and you've heard about a lot of information. You'll be curious. Some of you already probably have some idea, but essentially, it's like it's one of those strategic initiatives. Was actually starting in the Hanover Fair of 2011, was when this whole thing burst onto the scenes, when Germany came out with this concept called the Industry 4.0. Germany is anyway known as a manufacturing powerhouse and innovating in the manufacturing sector. They came out of this vision, what they call as Industry 4.0. And essentially, and associated with this is not the only initiative. There are also things like, you must have heard about in the United States, there's something called the Industrial Internet, which was propounded by General Electric Corporation. And Industry 4.0, by the way, is more focused on the manufacturing, primarily on manufacturing, innovations in manufacturing, how to make it more agile, more customizable, more flexible, driving efficiencies, etc. That's the goal of Industry 4.0 as propounded by the German industry. Whereas the industrial internet as propounded by GE was a much more broader canvas. I think it came out in 2012. They have actually talked about not only manufacturing, they have talked about transmission, distribution, and electrical system, electrical utilities, energy systems, then transportation, healthcare, and all this merged together. They have talked a much larger canvas for the what they call as industrial internet. Okay, and then there were other initiatives in France and UK and in China, etc. Made in 25. Made in China 2025, I'm told anyway. So, and then of course, to some extent, India has been more like a follower. Like we also adopting part of Industry 4.0. If you see, there are some companies which have adopted Industry 4.0 framework. So let me, without further ado, let me proceed. So yeah, a introduction would not be complete without a slide which shows you the evolution of this whole industrial and what we call as Industry 4.0. What are the antecedents to this? So as some of you already know, the first, if you can characterize it into 4 phases, and the first industrial revolution was essentially sometime to the latter half of the 1700s. And the primary driver there was that it used to be essentially a manual kind of a system still then. The technology had not progressed, and most of the things used to be done manually. So the point is with the invention of the introduction of hydropowered steam power, etc. That is when the first flavors of mechanization started coming. You must have heard about things like power looms, especially the textile sector was one of the first adoptions of this first industrial revolution. You must have heard of the power looms, etc., using steam and other mechanical power. So that lasted for roughly about a little over 100 years. I mean, no, rather close to the beginning of the 20th century. That classifies as the first industrial revolution. The next big breakthrough happened when the electrification, right? You have started, till then again, it was, even though you had power, mechanical power aiding in the manufacture, you still did not have things called the mass production, right? So that is when the electrification, the usage of electricity on a large scale is what triggered the second revolution. So I'm told that one of the examples mentioned is there was a slaughterhouse, I think somewhere, I'm not sure where, Chicago or what thereabouts, which used these kind of a assembly line concept for the animal, essentially the abattoir and essentially for meat processing. So they were one of the early adopters, and of course the infamous example of the Ford Motor T, one of the earliest automobiles which burst onto the scene. There is this famous saying during this phase about Henry Ford. You can have they were mass producing the Model T cars. So the famous statement, quote attributed to Ford is, "You can have any color of car that you want, as long as it's black." Okay, so that's a kind of a widely used quotation. What it essentially says is that you don't have much of customization. Products are manufactured in mass. There's not much of customization, and so that was what is characterized by the second phase of the Industrial Revolution. The third phase, as you see here, the timelines is somewhere to the beginnings of 1970s, is when the first program logical PLC controllers were introduced. I believe it was Siemens which first came out of their offering of a PLC. So essentially, you're talking about programmable logical machines, like where you can have configurable machines, right? And so the first phase, just coming back, first phase is categorized by movement from manual to mechanization. And there, the primary driver there was that the quality of life improved. Until then, it was very, very the dark ages. So people were working in very bad conditions. So that evolution to the mass production actually triggered an qualitative improvement in the quality of life. The second industrial revolution, as I already said, mass production started coming up. And but the problem was that you could manufacture a lot of things, but you could have no control on the quantity produced. Okay, you can mass produce at certain, but you cannot change at this thing. You have a fixed machines work with a fixed functionality, and they manufacture, right? And you can't customize. That was the second thing. The third part, the interesting thing was that when you have programmable machines coming in, you must have heard about NCs, lathe, numerically controlled lathes, and other things with embedded functionalities. You can have customization. You can start playing around with things, and you can start having customization built in. But still, they did not address the fundamental problem of quantity. You can still have a same assembly line which can produce variations in the product types, but still that it was not evolved enough to support the needs of today, where today it is like you need customization at an extreme scale. If you know the preference of human beings, right? The same assembly line may want, it's a Toyota Corolla, maybe of black. It may have a certain set of features. It may be a mid end of the Toyota, with some features. The next one may be a different color, some different features. So since these, as you know, this automotive industry, you have these different categories of offerings, right? So they, some of these are generalized, which can apply to any one of the, variants. But there are some which are fixed right at the time of manufacture. So these kind of things could be can be done when you have this flexible kind of a production methodology. And I'll come to that in a later. But anyway, I hope you've got this. So these are the 4 distinct phases of the Industrial Revolution. And so the fourth is based on what is called cyber physical systems. This is today what we're talking about. As I said, the vision was first put out in I think it was 2011 at Hanover Fair, and we are evolving down the way. I have an interesting video which I'll try to show you at some stage. So the interesting thing about this is that you have these what is called cyber physical systems. So as the term says, you have cyber at the interplay of cyber as well as physical systems. I will also do some definitions and stuff as we go along. So this gives you a broad picture of what are the kind of evolution of the manufacturing and production and the industrial revolution thereof. Please feel free to ask me any questions if you have. You can interrupt me, I can answer, or we can wait till the end of the session, whichever is suitable. So now just the drivers. What are the drivers? I already covered some part of it, but it is like that nowadays you have global competition, right? A manufacturing or this thing cannot exist in isolation. The name of the game is you need to have differentiated offerings capable of adapting to customer needs. Now you may ask, is this just a some key high-fangled words? It's not the case. Everybody is trying to do it. The company or the organization entity which is able to better service customer requirements is the one which actually need not be generally the best company wins. It may be companies which are more, I would say, integrated, sensitive, adaptive, and able to respond to customers are usually the winners in the marketplace, if you see now. Okay, so that's the reason why this global competition, fast adaptation, that means the market requirements are ever changing. So you need to have systems which are flexible, which are able to cater to these in a fairly agile manner. So essentially, as I say here, Industry 4 is a promising growth based on integration of business and manufacturing process. This is something you need to look at. So you're talking, one is the manufacturing process per se. We have talked about all the industrial revolution, all that. Second is the integrated business process. Like we know that enterprises do not exist in a vacuum, right? There are different enterprise functionality for even I'm sure if you look at just Jyoti, the engineering college, I'm sure you have different departments. You have the one is academic curriculum, the faculty members. Then you have, let's say, accounts department. You have the payroll department. You have the security department. You have the administration. Maybe you have a planning department. Maybe other thing, compliance, taxation, you name it, logistics, infrastructure. There may be different functions which are. So all this comprises to make what is called a enterprise or an entity, right? So essentially what happens, you cannot have manufacturing as a standalone entity. You need to have it, you need to have a complete, I would say, a holistic solution which is able to take all these inputs into account. And only then can you say that you have a totally integrated solution. So Industry 4.0 is actually looking at this aspect also, where you can meld the core manufacturing process also with the other core enterprise or critical processes which are there in the organization. And last but not the least, the supply chain. We don't just talk at supply chain, we talk of value chain now. One is the supplies. When you talk about, I'm sure in mechanical engineering, you must have heard about things like agile, just in time, Kanban, those kind of things. So you're talking of, more efficient, agile, where you are able to actually integrate your suppliers into your core processes. And you can have things like just in time manufacture, reduce your inventory. Like you have, you don't want to hold a lot of costs in holding a large number of inventory. They add to losses, it adds to damage, it adds to reduce revenue, right? So you want to optimize that supply chain. So that is also something which is catered to by this industry. It looks at value chain. How do you optimize that value chain? And the other part of it is the customer. As I already said, only one part of it is the taking the requirements, customer preferences, etc. Then there could be other thing. Are you able to meet your, do you have a responsive organization which is taking customer inputs, product feedback, product preferences, their sentiments. Like today you're talking about sentiment analysis. What is it, you put out a product, what are the customer feedback on the products? Are they happy with it? Or do they have issues? With the touch points of the company, are they satisfy the product features and offerings? So all these things are important. A holistic approach to looking at the company's offerings. So I think I'll not delve too much into it. Let me get into the hard core part of it. So essentially, as I said, Industry 4.0, we are talking about, we no longer talk about discrete system. We talk about cyber physical systems and what I call internet industry of things to industrial production system. So what do we mean by cyber physical system? I'll delve at it a little later on. So essentially what you're talking is, there is a core, something called execution systems. Okay, as I said, the execution primary thing, we don't no longer call it just machines, we call it cyber physical system, cyber and physical, right? Where you talk about embedded, intelligent, autonomous systems, a system which has both the physical elements as well as the intelligence, ICT and other logic and thing built into the system, as well as communication using the IoT. So this is what is called cyber physical systems. So these blocks are one of the important points is that you have, let me just take 1 minute off. See, earlier systems were what is called as fixed production systems. That means you have a line, you have machines and or other resources which have fixed functionality. They cannot vary. So they can only do what features they have. Maybe it's got a milling machine or a lathe or whatever it is. They could only do that function. You cannot do another task with that machine. So your per se, your job scheduling and thing is constrained by that this thing. You cannot, it's not flexible. The next thing which came about is what I call flexible production system. Flexible production system where you have software, I talked about PLCs, program logical controllers. You can have flexibility in this, and the same thing can do multiple things based on programming, multifunctionality. And the most important part is now is called a reconfigurable manufacturing system. I will show you a slide which will actually give you further idea what it means. Okay, so before I get there, let me just cover this part. So as I said, there is a manufacturing execution system, and then the core functionality of enterprise is something called an enterprise resource planning system. And last but not the least, the big thing is the most important part of this is the data part of it. So you need to have, you need to be able to generate the data, collect the data, store the data, process the data, analyze the data, and probably take corrective, take actionable insights based on it. These are all the things which is most important. The data, as they call, is the new oil. So let me just, without further ado, let me show you a video. I hope it's able to present itself. One moment, where is that? how do I close this menu bar is obstructing the tabs. Is it possible to close the menu bar? Okay, I'll try to put a standalone version of it. I hope it displays. For some reason, that tab is not getting displayed here. I hope you're able to see this.
Yes, sir.
Just let me know if you're able to see it.
Yes, sir.
and you were able to listen to the things? Hello?
Sir, actually, the video, we couldn't see the video.
Oh, you couldn't see the video. What happened? Video was not visible?
No, sir, actually, only the slide was visible.
Oh, okay, okay. Oh, I wish you had told me. One moment, just a minute. Let me see. I'll try to play it and. Oh, okay. That's because the video is very good. See, this thing is not closing actually. This is not. I'm not able to. All the tabs are right on the top, so I'm not able to view the tab here. It's coming. This menu bar is locking it. Otherwise, I had a browser window open with the what do you call it? That YouTube link. So I'm not able to do it now because this menu bar is sitting right on top of it. Can you just shift that menu bar from the top to the sometime to the right? In which case I'll be able to open the tabs.
So actually, I think it is from your side, sir.
Oh, is it like that? Okay, so let me see. I'll try to do one thing. Let's see, can I do that? No, I think I'm not able to.
Otherwise, you can do one thing, sir. You can press the window button symbol along with the D together, so that you can change the tabs.
Oh, Windows sign plus Alt tab, is it? You're talking Alt tab?
No, sir. Windows symbol plus D.
Plus T. Okay, okay,
Windows
okay.
D. Windows plus D.
Okay, okay, okay. Just a minute. Am I able to see it?
Desktop.
Okay, I'm not. That particular tab is not coming. Okay, it's not coming. Okay, anyway, let me. Oh, you're not able to see it. So then that's unfortunate because that video is very good actually. So how do I show that now? Is there a way to show that video? Can I show you the link? You can just put the. See, the link is as follows.
Okay, sir. You can do this, sir. You can put the link in the chat box so that we can.
Yeah, here is. Are you able to see this link now? In the
chat box.
Oh, on the chat box. Okay, 1 minute. Where is the chat box? 1 moment. It's there, is it? In this one? Where is the chat box?
Sir, the bottommost portion you can see a chat symbol near to participants list.
Oh no, I'm probably seeing a different interface, so I'm not able to. Okay, okay. Chat box. This one. This is the one. No, I think I'm not able to see the interface you're talking about. So anyway, let me just proceed. So that I think there's so many people there, so we'll try to sort it out. So let me just proceed with the presentation. Maybe towards the end we will try to cover up the video if it's possible. Okay, so I think it's unfortunate not able to see it. Many important concepts are brought up in the video, but let me just without ado, let me just cover. This is what is a simple slide. I've copied here, which is called the smart factory. So the smart factory is a core of the almost entire functionality of what we're talking about is captured here. So if you see the bottom half of it, you have this what is called the digital to physical conversion. So that's a core part of it, where you have digital to physical conversion, where you have. I already talked about something called a reconfigurable manufacturing systems. Okay, so essentially, I talked to you about fixed production system, flexible production system, what is reconfigurable manufacturing systems composed of primarily what is called as cyber physical systems. Like cyber physical, what you have is these are the difference of cyber physical system is that they are mostly decentralized. They are traditionally you used to have what is called as hierarchical production systems, which are more or less rigid, top-down kind of things. The key difference with this is, as I talked about customization and flexibility, right? The key part innovation here which has come about is what is called as decentralized and autonomous systems. Systems are intelligent enough to communicate among each other, take decisions on their own in a collaborative form, and control and organize the machines, these systems, to achieve the end objective. So that's a key innovation here. So typically what was actually shown in the video also, which I will just articulate, is that systems are able to communicate with each other, right? So what happens is, let's say there's a product which is being manufactured. the systems are in constant using the IoT and the wireless communication gateways. They're able to communicate amongst each other, modify, decide which of the, the kind of systems are to participate in the production of that. What is the pathway to take? What is the, what do you call it? The logistical pathway to take to manufacture the system, designed on the combination of systems required to manufacture the product. So as you see, a lot of hitherto all this was done by human beings sitting there and deciding, making decisions. So here we are talking of smart systems which are able to actually they have all using, that's only one part. The one is the complexity, they are able to have intelligence. Second is that they're constantly monitoring, getting data feeds through IoT to sensors, etc. They're getting data, analyzing the data, and they're able to make changes on the fly. So that intelligence is built in. So this is the key thing, innovation which has happened in these, what is called a reconfigurable manufacturing system. And last but not the least, you have, you have things like collaborative human and machine collaboration. Like there are some, you cannot, as you probably well know, all tasks cannot be automated to 100%. So you need, there are maybe design tasks and certain other tasks which are not fully structured, where you require a man and machine to work together. So in which case you need what is called as human machine collaboration. You may have heard about, you may have had courses, in robotics, but we're talking of something called collaborative robotics, where a man and a machine is able to work together in a collaborative manner. So there you will need interfaces and mechanisms to do human machine collaboration. Obviously, when machines are communicating with each other, you need M2M capabilities, machine to machine. You have human to machines. You have advanced interfaces. Then have things like interfaces using things like virtual reality, augmented reality, etc. Then we are talking about innovations in the last few years. Concepts like additive manufacturing burst on the scenes. All this together all fit into the scheme of things, which is called Industry 4.0. As we mentioned here, on the right side, we talked about decentralized, modular, autonomous. That means they can take decisions on their own, right? And self-optimization. As I said, they're able to, you don't need a human being to write the job schedule and figure out everything. They're able to have the intelligence to figure out, you have machine learning and algorithms built inside, which can actually constantly using the sensors and data and capture, they're able to optimize and come out with for reduced cost and for optimal manufacturing. So that's as far as the digital to physical conversion. You must have also heard about things like digital twins, etc. About a mechanical artifact, you have an equivalent, which is digital, which is an object in the cloud. So that's the physical. People use the word digital twins, for instance. So typically what happens is when you talk about digital twins, you're talking about things like 3D models. You're talking of maybe drawings. You're talking probably test data. You have probably the whatever component you're talking about, state. Like as you put out a product in the market, you have things, the environment, the interactions, that state changes. So that data needs to be captured inside as well. So that is what you're talking about, digital twin. Okay, so now let's just quickly brush across the other thing. We talked about business analytics, data analytics. I'll talk about it later on. Then I've already talked about supply chain, right? Supply chain, how do you optimize? In the era of optimization, you want to optimize your supply chain. I talked about things like just-in-time, and just-in-time manufacturing, Kanban, and by the way, I'm sure many of you are from mechanical engineering. You know that logistics comprises a very large cost of the end product. So if you can achieve optimization logistics and supply chain, you can actually a lot of cost savings for the end product. So that is where the supply chain, I talked about value chains and how does the system able to take care of the customer and the value chains as part of your overall manufacturing process. Mass customization, on-demand production, marketing and services, etc. Okay. So this is a well-known automation pyramid, in modern production systems. Shanmugesh, are you covering these courses for your undergrad students? Something related to production systems and these kind of things like manufacturing execution systems, etc. in your academic offerings? Shanmugesh? Okay. I think he's not there. So again, this is the classical automation pyramid in production systems. So if you remember correctly, when I started off, I said we are looking in Industry 4, we are looking at actually harmonizing the business process and the production processes, correct? You want to analyze in an enterprise, you cannot have these in isolated silos. So you're looking at having a system which is able to encompass the entire set of activities. So at the top end of the automation pyramid, you have something called the ERP. I already talked about enterprise resource planning side with all the enterprise functions. Then below that is what is called the manufacturing execution system. So things like job scheduling, the planning part of it, the logistics part of it, the reporting part of it, and all those things will come into. Ultimately, the ownership of that is in this process called the manufacturing execution systems. Then as you go down, you're kind of down and down to the physical layer. And finally, you actually, you have the production, the individual machines or components or workstations. Then above that, we have something called the PLCs and the programming controllers, etc. And then you have, above that, you have things like SCADA, human machine interface, etc., and MES and ERP. So this actually constitutes what is called the production system automation pyramid. And here, these are the different kind of systems. So to achieve the kind of flexibility and expectation of an Industry 4, you need to have both information. There are these different systems. You need to have vertical as well as horizontal flows between all these different what I call modules, the SCADA systems, the controller system, ERP system, robotic control. I talked about human machine collaboration, correct? CNC, you have the programmable logical machine, the machines, programmable machines, PLCs, virtual robot control. All this, since there are so many different modules, you need to have a capability for free information flows from these different in the cloud, these data repositories in the cloud. So one of the drawbacks in the hitherto was that we have, I already talked about this automation pyramid, right? The manufacturing production, the automation pyramid. We have something called the OT data, OT operation technologies, and the IT information technologies in this pyramid. So typically what happens is hitherto, prior to Industry 4, you had these different silos and lack of integration. They have the different systems. Typically, they are all in different, silos, and you don't have that level of interchange or collaboration to really achieve optimization. So these was some of the drawbacks hitherto in the manufacturing process. The SCM, the supply chain management, the CRM system, independent systems. So you don't have a seamless connectivity there. Customer data is not this thing. Supply chain data is actually not integrated. So which actually leads to a lot of inefficiencies. So I'll not cover this. This is actually a framework which is actually put out at IBM. I'll not cover this. I will actually just skip this for the time being. So let me just talk about, we talked about so many of these things in earlier. So there are these, what is called a building blocks to really achieve the true capability of Industry 4. You have these different legs available. Obviously, big data analytics is one core area. Then you have, I talked about additive manufacturing here. Industrial Internet of Things, basically IoT, industry of things, industrial Internet of Things is a key enabler. You have to have system integration, different I talk about different systems like a supply chain, ERP system, MES, and different robotic systems, etc. You need to have systems which actually allow the free integration in a flow of the information. You have autonomous robots. Then you have additive manufacturing, augmented reality. That is also very important. I'll try to, if time permits, I'll try to show you an example of that in one of the succeeding slides. And of course, obviously, big data analytics. So yeah, let me just cover into some parts of big data. We are actually talking about data which is from multiple sources, actually, right? I'm sure some of you know the definition of big data. What are the big definition? One of the definitions says data which is actually larger than what a physical machine can actually process. Another definition talks of the widely used definition, 3 V's, 4 V's, etc. Velocity, veracity, variety, volume, etc. using for the big data. Okay, so all these definitions go to characterizing the data sources as big data. Please understand, we are talking about zillions of IoT. We are basically instrumenting machines and mechanical artifacts and processes which hitherto were lying as silos. We are actually instrumenting it, with sensors, the cost of sensors have actually gone down drastically, and the energy requirements of sensors have gone down. Sensors and actuators are now become very small form factors. So you're physically now capable of incorporating sensors in different physical and manufacturing processes. So with the instrumentation of sensors into so many diverse process areas, you see you have to have an explosion of data, because all of them are capturing data and sending it out. So just imagine you have hundreds of thousands of essentially like the video feeds, the sensors, maybe the speedometers, the accelerometers. Just talk of your simple your mobile phone. It has accelerometers, maybe a gyro. Some of them do have gyroscopic capabilities, accelerometer, cameras, videos, and your accelerometer, motion sensors. So many sensors are available. So what happens is your simple thing like a mobile phone, if you have all your things on and then you walk, you generate huge amount of data. Look at it from an organization. When you have so many machines and people and processes all working, the amount of data which is coming out can be humongous, and depending on the size of the organization. So essentially, we are talking of a big data kind of scenario there. Data coming in different things, like you have volume, veracity. Volume is the size of the data. Variety, different types, structured, unstructured data, etc. I think I have some slides. I'll also cover that in future. So you need to have, one is generate and ability to store and process the data. Second is that you're able to do processing on the data and interpret the data and be able to do things like analytics. That is where the key value proposition comes in. Okay. So you need to essentially, to really exploit the value, you need to be able to usage and exploitation of big data. So I already covered it. We are talking of high volume, high velocity, variety, structured, unstructured. And structured data, as some of you already know, is which comes in, essentially hitherto in an organized form in what is there in database systems, which are structured. You have a schema. So you have data which are all structured, and all data conforms to what is called a schema. They're all having a particular structure, every data type. Like for instance, you have an Oracle database, for instance, you may have an integer, a float, or any other device, numeric or a character set, etc. These are all structured data, correct? So that is one type of data. But then you have so many things like these sensors, and nowadays a lot of integration of social media data comes in directly, right? You have feedback on products. So these typically come in the form of social media posts or blogs or whatever, or posts. So these are typically what is called unstructured data, where it doesn't have a fixed schema, but it comes in either no structure or minimized, or not a well-defined structure. So these are called unstructured, or in the form of images, etc., which don't have a structure, like what we talked. So you need to be able to process these different kinds of variety of data, high velocity. You not only have static data, you have streaming data, right? These sensors are capturing in real time, virtually real time. They're streaming the data, etc. So you have volume. Volume is the amount of data. So as you said, structured, unstructured data, thousands of terabytes. Okay, terabyte, what is it? 1000 to the power of 3. Okay, 1000 to the power of 3 is terabytes. So you have tens of thousands of terabytes. Now people are talking petabytes, which is like 10 to the power of 1000 to the power of 5. And on top of that, you have these things called volume, variety, velocity. Now people are also talking something called veracity. It's a trusted data, and that line people talk about blockchain and trust architectures, etc. But again, these are all some of the things which add to the complexity. You have one is a structured, unstructured. That is the variety part of it. Then you have the volume part of it. Then you have these variety, volume, velocity. This is just an example. This is not the most recent data, but then just to give you some idea about what is the amount of data we are talking about. Just a simple example of a Google search engine. Like we are talking, this was data. Now it will be probably some factors more than this. At that time, I took this data. It was 2 trillion searches per day. Okay, they have a lot of indexing. Literally anything Google has index, you can do a search on that. Now, another large example of data is Walmart. You have so many different stores, different point of sales terminals, thousands and probably hundreds of thousands of products, millions of customers dispersed across different geographies. So you can imagine the amount of data which is actually generated. Like at that point, they're talking of 2.5 petabytes. Petabyte is, as I said before, 1000 to the power of 5. So imagine the scope. Gone are the days when you're talking of megabytes. I still remember when I started my career, if you had a few megabytes of, it used to be called big memory, your computer memory. Now this laptop I have itself has a few GBs of RAM and probably a terabyte of data, a terabyte of storage. And these are just a very entry level or just a basic level laptop. You have much more powerful systems, things like GPU powered systems and high powered, compute intensive and high storage data available. So another example here is talk of for Facebook. I think some of you already have probably accounts in Facebook for photo sharing. Those, imagine you can have so many billions of photos being shared. eBay, again we're talking petabytes of data. And adding data. Then, of course, a classic example was scientific is the CERN's Large Hadron Collider, CERN, European Energy Institute, which is actually doing research on atomic, subatomic particles. They actually simulate these collisions at a particle, subatomic particle level and do fundamental research on physics. So they have to set it up and do a lot of processing and do a lot of particle analysis studies. So it generates huge amount of data. Another example could be systems which actually look at astronomy, the stars, the galaxies, and this thing, analyze the space and the constellations. These are all generate a lot of data, actually, the astronomical telescopes. So coming back here, we are talking about Industry 4. We are talking at the fundamental level, at the atomic level, you're talking sensors, actuators. Then these are all kind of shop floor, etc., in the factory. And then we talk of integrating that to the value chain, the customer, the suppliers, supply chain, etc., etc. All this, and then you're essentially all this. You actually collect the data, and typically in the cloud. Of course, people are also nowadays talking about edge processing to do some wherever immediate small level analysis analytics. You're talking processing at the edge, but typically at a large scale, you're looking at data which is actually pumped into the cloud, and you do the storage and the processing in the cloud to process the data, and you do analytics on the data, reporting, and you get actually actionable intelligence and inferences are generated thereof. So this is again just a slight aside here. Just to give you, since it's about analytics, I wanted to just give you must have heard about some seminal developments. How did this Hadoop and all these file systems evolve? So essentially the starting point for all this is Google published 2 papers, one on what is called the Google file systems, and which is basically the storage part, and the MapReduce is the processing part of it, distributed processing framework for processing large amounts of data. Because Google found that they were not able to use the conventional file systems, like your NTS network file systems and your other. They were not actually very efficient in processing, what is called big data, and the different. I told you about big data, right? It has different characters, variety, velocity, all this thing. The existing file systems and storage and processing frameworks were not really good at processing these kind of in the big data age. So that's when they start about with these papers. They publish their approach towards a new kind of a storage and a data processing framework, which actually is the starting, which is actually recognized as the starting point for all this big data, real big data analytics and innovations. And so what happened, as if some of you are following it, you would realize that when Google published the paper, there was this the Yahoo was actually working on some open source projects for essentially web indexing, etc. And duck cutting here, who's shown here, realized that this is exactly what he wanted. When you talk to indexing, you're talking of massive amounts of data indexing web pages. He realized here is a solution, which is the approach paper which Google put out, is actually kind of meeting what he's looking for when he's wanting to do this vast amount of indexing. The kind of technical requirements what he was trying to build in-house was being actually being satisfied with the kind of approach paper which was published by Google. So they went about developing in an open source, developing as per the specifications given out the Google file system and MapReduce. They actually the earlier one, which is called big I think it is called Big Table, and I forgot the name of the processing system. They actually go ahead and develop it, and it came out as an open source thing called the Hadoop Hadoop storage and MapReduce data processing framework. And this was actually incorporated as an Apache Foundation project. And so now it has kind of Hadoop. Like if you see the left side is when the papers were published, 2003, 2004, 5 was when the Google file systems implemented, and then Yahoo open sourced it, and then you had things like the core Hadoop, storage and processing framework comes out, and then a lot of utilities get built. See, they realized that you cannot have a very arcane system which actually was difficult to use. So people realized that a lot of people who want to do analytics etc. come from an SQL kind of world, relational space. So they created an interface where you can have an SQL-like interface, SQL-like interface to do data querying, processing, etc. So a lot of new utilities got built on top of the SQL base. You have different SQL-based systems and etc. sitting on top of the core Hadoop framework. So more and more utilities have got built up, and that makes different people can actually start using the Hadoop framework, and also things like more things like machine learning and the columnar databases. As opposed to RDBMS, you have things like columnar database, etc., which came in, and you have more and more. And then, of course, the Spark framework, which came out, I think, came out of Stanford universities, which actually radically in-memory computing. And one of the drawbacks mentioned for the Hadoop system was that these are like batch processing systems, which are good, which have fairly good throughput, but then it's not, it takes a long time also, right? So all jobs, all physical problems may not be amenable to a conventional MapReduce kind of a modeling. So what people did is that they came out of this Spark framework, which has achieved much, I would say, much faster throughput in memory processing. And many of these vendors, like your SAP and others, they come out with the Spark engines, which actually in memory with massive amount of in memory capabilities, they're able to do a lot of processing in memory without basically doing IO and hitting your persistent storage. So you have so many things coming out, and then you have the developments on the front end. You have R. Some of you may have used R, statistical analysis package, which is open source again. Then you have Weka, which came out of the University of Auckland, which again their their statistical and what do you call it? You can do data science projects using Weka. Then Pentaho and others, which came out of the vendor space. Tableau is one of the key things which are for visualization of the, when you do analytics, visualization, and you can do that using Tableau. So these are some of the things. It's not the entire list, but these are some of the list of vendors which have actually built their solutions and/or things over the. Of course, the columnar database HBase was part of the early versions of the Hadoop, where you can do a lot of people have realized that for a big data kind of thing, the RDBMS relational database data model is not schema is not necessarily the most efficient way, and so they've come out with what is called a columnar database, of which HBase is an example. Okay, so these are some of the ecosystem components built on top of Hadoop, and Hadoop is evolving. More and more things are. You have different variants by Cloudera. Version of Hadoop. Then you have Apache, which is core open source. Then you have Cloudera, Mapr is one of the vendors. Then you have Hortonworks. There are different vendors who are building their offerings, big data offerings, more or less built on the core, which is Hadoop, but they have built their own customized offerings on top of it, based on the for performance improvement and as well more capabilities. So here, just a quick thing. The fundamental difference, as many of you realize, is that as opposed to RDBMS, where you have a schema and you enforce a schema. So when you actually try to put in data, if the data is not conforming to the schema, the data, the system does not allow you to store the data, which is a probably very constrained model, because in the big data world, you have streaming data and data from different sources where you may not have the schema information or structured information all at once. So previously, when you did not have capabilities, you end up, if you don't have a schema, a lot of data gets thrown out. You can't see fundamentally when you're collecting the data, you may not immediately know what you'll do with the data. Some of the data may be useful, but unless you look at the data, you don't know whether it's useful, right? So since you do not have capabilities, many times data used to be thrown out. And then another example was these massive data warehouses, which are very expensive. So the storage and all is very, very expensive. So you can't, again, you have limitations. my data, what you call data lake or whatever, generates tons and tons of data. But since my processing framework itself has limitation, B, storage is very expensive. I cannot store the data. So that is where the key thing, what is called, they have come out with something called a schema and read. So you have fairly, I would say, what is the word to use? Less rigid kind of scheme where you say, I allow you to store the data. I don't enforce a schema. And only when I write, when I write the data, when I actually store the data, I don't rigidly enforce a scheme. So it allows me to dump data into what I call a data lake or a storage, big data storage. And when I read it, I can actually impose a schema and do it. So this is a much improved model for a big data kind of scenario where I don't have to throw away the data, but I can actually wait for till such time. So and I don't have to actually I'm able to store the data and then figure out a mechanism of how to analyze the data. And so this is just a small schema. I thought data science process, this is the kind of I think the workflow, if I might. You determine a problem, you collect the data, you explore the data, analyze the data, then you can access. When I say storytelling is where you actually, your interpretation of what is you present your result, take action. So this is the kind of flow in the data science flow. And this is again the same thing. Okay, some of these processes I do not cover. Things like when you have data engineering, one of the key activities, which is not much of a value add, but is very important, is that formatting and cleaning is very important, because data sources may be incomplete, they may be corrupted, there may be noise, it may be coming from different sources, there may be missing data, there may be wrong data, etc. So you need to have all these things done here, right? And the other is integration part. When you have data from different sources coming in, you need to integrate it, and that's a probably difficult. See, simple example, you may have duplication, right? Let me just give you one very practical example, right? When you have in India, you have one of the biggest projects is the Aadhaar projects, right? The homegrown, what do you call it? Identification, citizen identification project. We have, just think of it, more than a billion people's biometrics and other data is collected. And the difficulty, it's not just so simple that you go to Aadhaar center, you store it. Even before this, you have the NPR database, you have the PAN database, you have the Godel owners, what are the databases, etc. sitting, the different databases are built up. And so what has happened, the government must have faced a lot of challenges trying to integrate the data. Aadhaar database, NPR database, your PAN database, then database from other sources, etc., and integrate it. And finally, so just imagine that just to show you the complexity available when you have these different data sources. So when you over and about that, let's say you talk about IoT data. IoT, you have, maybe till recently there are not many standards, so different people have different components, different devices, different sensors, each generating data in their own probably what do you call it, proprietary manner. You can just imagine the challenges involved there. And so this is just a slide I thought, I'll put it up. Analytics, as we know, is not just one buzzword. You have different. You look at it in terms of complexity and in terms of value add and in terms of evolution. There are different. The earlier dates using statistics and all this is called descriptive standard, where you have, summarizing data or using some, things like you are able to describe the data in terms of averages, in terms of measures of central tendency, etc. You're able to show it. Then diagnosis, which is just a slight variation. You are able to do diagnosis, called diagnostics. Now, the current kind of thing is mostly spread about something called predictive analytics, where you have things like machine learning and regression model, statistical model, where you can actually, based on historical data, you can predict, etc. I'll give you one or two examples as I go forward, but you're talking of predicting. Like a good example of this is the weather prediction. People say, like, if you look at both maybe channels, Kerala or international or any channels, the IMD, they're able to say that 2 days from now, cyclone is going to hit, there is going to be rain, so much of rain, so many wind speeds. So that's an example of prediction. Another example where people do is that, let's say a utility, which has electricity, load dispatch, you need to predict the demand. You cannot just generate on the fly. You need to have ways of generating how much of demand is likely to happen, how much should be my generation for the day. So that you try to mix and match. Otherwise, you may have load shedding, or you may have excess capacity brought online and there's no demand, which will cause losses, right? So there is a predictive element there as well. Okay, so how much of generation capacity you have to bring? You have different generation, like you have thermal generation, nuclear generation, hydro generation, maybe renewable generation. So just imagine the complexity of this. So you should be on the one hand try to meet the capacity, the demand. On the other hand, generation capacity, and B, last but not the least, complexity is that the energies are of the energy sources are at different levels of cost. So you need to plan what is the optimal level. How can you do things like demand response? Can you do load shifting? The Kerala, we are very much aware of it, right? Load shedding. Sometimes the thing goes and then the power goes off. So can you prevent it? See, if you go to the West and all, it really doesn't happen. I was there for a project overseas. Not even once there was a power outage. Whereas here you see every other day. Yesterday, like my session was supposed to be yesterday, but the entire day there was no power. So this is an example, like all this will help. Predictive analytics will help a lot when to actually balance the supply and demand in an intelligent way. And last but not the least, the highest level of this is what is called prescriptive analytics. Can I use my data and my intelligence to actually prescribe what is the best course of action? I'll just give you there is a slide which probably explains it. I'll try to going forward. So I've already talked to you about this predictive analytics using historical data to predict future outcomes. What will happen? I give you some examples of weather and load dispatch and utilities and stuff like that. Another example could be in retail stores, stocking example, right? Typically Walmart. I'll give you one very interesting example. I don't know how much time we have, but Walmart, I read a case study which came in, I think, Harvard Business Review somewhere. So example is like, I'm not sure it's Target or it's Walmart. So apparently they found out that, there was this, when a cyclone or a typhoon hits or a hurricane hits. So typically what happens is the entire life gets affected, and people kind of, they're probably immobilized there in the houses. And so they found out that using some of the software, they found that when such events happen, the consumption of certain items shoots up. So like a cause and effect, like when this happens, this happens. So what apparently happened is, I'm not sure it's Hurricane Katrina or some other thing. They use this, actually physically use this. They found that the weather patterns predicted that this is going to hit certain parts of the United States. So what they do is this, let's assume it's some food item or some other item. So let's assume the finding for Walmart or Target was that when this happens, this item gets consumed. So that's very valuable information. So when they predicted this hurricane was going to hit these parts, the Walmart or Target, whatever, stocked those stores in the path of the hurricane with all these items, and they found that as predicted, the demand for those items rocketed, and they made huge profits. So this is a classic example of how you can use prediction algorithms to actually profit from certain happenings. Yeah, so predictive increase value to the customers. Predictive analytics. Yeah, one of the key use cases is like, can you have as opposed to just a failure maintenance or some random time-based maintenance, can I have something called predictive maintenance, right? That means can I predict? Do I know? Let's assume there's a lathe or a numerical control machine or some machine, maybe a milling machine or a grinding machine or whatever it is. Can I, one, I would say not very intelligent way of doing it is, I say every 6 months or every 3 months, I will do a maintenance. But if I have the intelligence, let's say the machine miraculously have some capability of informing you that this is my state of the machine in so and so month or 1 month or 2 weeks or whatever, these parts are likely to wear out and they need to be replaced. If the machine is able to communicate that to you, that's valuable information. You can actually utilize your asset in a much better way. You don't end up doing maintenance far ahead of time, far before time. You're able to exploit the asset to the maximum usage possible. And just before the occurrence of that event, you're able to do your maintenance. So it's a very valuable, I would say, capability. So let me give you an example. Like when I was in Toshiba, this was a classic example which came. So they were, as you probably know, some of you already know, that Toshiba was one of the, they used to make all these MRI and scanning, ultrasound, and many, I would say, fairly sophisticated medical equipment, scanning, MR scanning, and all kinds of different sophisticated scanning, body and brain and all these things. So the problem with that is that as opposed to mass manufacturing, these are highly expensive equipment. They're more like discrete. You put an item and you don't need to, assuming the equipment stays, it doesn't get damaged. You can stay for normally for the lifetime, and then you replace it or you change some parts. So these are not mass manufactured. So you can't have a shop floor dedicated to going on manufacturing these things. So there they came out, we had an R&D set up in Bangalore. So one of the problems the corporate gave us was that we have these machines. Can you predict, given some set of data, captured data, can you actually predict, write a model which will predict in 15 days time, what is the, which is a, let's say there's a magnetic coil in one of these scanners, and that was probably one of the most critical items in the scanner. Can you predict the failure of the scanner 2 weeks in advance with maybe 60 or 70% accuracy, so that we can actually ship that part across and replace it? So you can imagine, right? You have a, let's say a hospital or a facility, medical facilities having these scanner, expensive, maybe $1 million scanner, and you don't have huge number of that. They are manufactured just when they are required. So if you can actually build a machine learning solution, which can actually physically use the data which is coming out of the captured from their different sensors, like heat information, voltage information, maybe other image, and maybe something else. Apply statistics and machine learning and come out with a prediction of when it's likely to happen with lot level of accuracy. Then this is, so this was I brought up this example just to give you a feel of what are the kind of real world problems. I already talked about demand for electricity, etc., where you can have resource planning, scheduling of power plants, etc., where you can use these predictive capabilities. And so just an aside here, is that we have you have different machine learning itself. You have broad categories, something called supervised learning, unsupervised learning. Supervised learning is typically where we have example data, things like regressions, classification, etc., etc. These are decision trees, etc. are kind of algorithms or methodologies you can use for supervised learning. Then you have something called unsupervised learning, of which typically things like clustering, etc., are where you don't have example data and you can actually apply these algorithms to find insights from your data. And just to give an example, like yeah, this is a beautiful the aerospace. I'll just dwell on it. I think we have about 15 minutes, right? 15-20 minutes, so I'll try to just bring it around. See, aerospace, I was just reading one of the very interesting article, like GE, General Electric has been one of the large manufacturers of aircraft engines. See, aircraft engines, as you realize, are very complex systems, and they very cost a lot, and you really need to have a know that, and failure is absolutely should not happen, right? Because the cost of a failure is so much. Plane may crash, lives are lost. So they are one of the really important users of these predictive analytic capabilities, and on the forefront of using all, because there are tons of data generated when a aircraft goes for one flight. There are so many sensors in the aircraft, engine and this and that and rudders, all your different what do you call meters and different surfaces, and you're capturing data, your wind speed, your temperature, your this thing, your engine vibrations, RPM data. So many data is captured. So they generate tons of data, and they use these machine learning techniques to actually predict, and they're actually using it to schedule your maintenance and also replacements and stuff like that. So for every system that they have a complete history of that aircraft cart is maintained, and so much so that General Electric, they claimed that they had built up so much of competence in engine manufacturer maintenance that they were able to give people different models. See, the conventional model is you buy an aircraft, you buy the engine, that's it, and it probably get into some kind of an AMC for maintaining the engine. But GE, since they're doing very powerful analytics on that data, they came out with what are called leasing models, where they say you don't have to buy the aircraft. You just pay based on your usage, pay per usage, like so many kilometers, so many dollars. So just imagine, it's a very powerful model, right? For the manufacturer, it's for the what do you call airline, it's a very good model because they don't have to pay upfront entire cost of the aircraft or the part of the engine. But it is for GE, it relates, it gets more business. But the flip side is that if the see it depends on machine usage and engine usage, etc., etc., right? So if they get the model wrong, see, you have to price it. The important thing is pricing. The pricing is critically based on analysis, how much to charge. Maybe some airline has got a very good safety record. They use very good pilots. They have very good quality procedures. And as a result of that, the engines typically last long. Maybe there is yet another airline which has a lot of failures, don't use probably good pilots. The pilots are not skilled. They use not in a very good way. They cut corners. They don't maintain it properly for cost reasons, and a lot of failures happen. So you need to have a different pricing for these two different, right? For the first blue chip airline operator, I would probably like to give a better price offering. Whereas in the second one, there is a risk is more. I'll give a more maybe different kind of pricing. All this can be achieved using very good, as I said, algorithm which can actually give you the prediction capability. So financial services, all of us know, right? Especially during COVID, people say that the fraud has, credit risk, fraud, etc., has improved. So cybersecurity and this, you need to have capability. Customer, is a customer likely to default? If you give him a loan, is he likely to default? All this is a part of the credit risk prediction. Also, that I already talked about machine failures and maintenance. And I already talked about that. So I think I'll not delve on this. I've already talked at for this. So the setup is something like this. Typically, you're looking at you have the shop floor and your machines and on the left side. You probably have a data cluster, right? You don't gone are the days when you have single machines. You already talked in clusters or data centers. You actually import the data typically in a cloud or in-prem. Then you have machine learning where immediate real-time this thing is, you have real-time machine, real-time analytic, data storage, then prediction alerts, etc., etc. And then you can have all these output like predictive material planning, you can have quality management, production line maintenance, production quality assurance. These are some of the things which come as an output. Excuse me. Yeah, so here is an example. I think we have just about.
Excuse me, sir.
Yeah.
The previous slide, can you talk about that speed?
One moment, just a moment. What is that?
Speed capacity.
Where is that? Stream data cluster is. Oh, speed. Oh, okay. This is like speed capacity is how much of the events, like these typically are what are called events, right? See, so you can actually, okay, let me give you a very mundane example. Like events, you know what an event is, right? So let's say, for instance, you have what is the word to use? I'll give you a very mundane example. Let's say you're using a laptop, correct? So let's assume that it says that your battery is drained, for instance, right? My HP laptop is able to do that. When my battery reaches some 10% of full storage.
Your sound is getting.
Okay, is it okay now?
Yes, sir.
It's better. Okay, I had just pulled it down. So, so the thing is that it is all some intelligence you can build into. So there are agents on these systems which can actually give you raise an event, an alert. Okay, an event could be something. Let's say one event could be, okay, let's assume I had a spike in the electric. That could be an event, right? My electricity supply is serving. Let's say my objective is quality of power supply. I don't want frequency or some spikes coming. So let's say I have one spike. Let's say there's a lightning or something happen. There's a spike happening. That could be treated as an event. Another event could be, another example event is, let's say I have a laptop. I'm booting up the system. And so it does a lot of processing, right? The booting has a particular ordering and this thing. It notices anything. It puts out events in a log. So typically these events are logged. And by analyzing these event logs, a lot of intelligence can be made. So typically in diagnostics, right? You are looking at, let's say, machine failure. You want to, let's say a machine in a factory shop floor has failed. and you want to do diagnostics. So first thing a person does is that they go to the logs. Aside from the physical examination of the machine itself, and probably some interviewing, questioning the operator, etc., you also look at the logs. So nowadays, since all these systems are instrumented, you have these logs. You can actually look through the logs and try to analyze the logs to come out with cost-effective kind of a scenario. So let's say you have typically things like fishbone analysis and Six Sigma policies, right? Where you actually do cost-effect analysis. You're able to do causal analysis and try to find out, let's say if a turbine blade has broken, maybe your theory is that maybe the speed RPM has, RPM has increased or the load has decreased, and there is a high RPM because of the reduced loading or fluctuation in the load, or maybe some vibration happening as a result of which maybe there was some the shake happened and that it probably hit the casing or something and broke, whatever. So I'm saying that to do a causal analysis, you can actually analyze your logs and the usage patterns of your machinery, and you can actually do your cost effect analysis, and that is where these events. So when you do this, so this here is a capacity where we are saying so many events can be processed. Okay, so let's assume that so many blocks of data is being received, correct? So this probably has a throughput of, I'm just giving some, offhand I'm thinking through. So it is able to process that many. The throughput of that system is that it can process 15,000 events per second. So if it exceeds that, it may not be capable of, it'll probably not be able to process. So up to 15,000 events are generated from different, let's say, devices, IoT devices and other things. It is able to, and it is streaming it across into the cluster and the cloud. So it's able to process at that thing. We talk about, right, when we talk about a network, we talk about so many Mbps. When you talk about an internet system, you talk about 100 Mbps. I have, let's say, 2 GB per day. So there's a lot of capabilities, right? So similarly, you have this cluster is able to, in this particular scenario, is able to process 50,000 events. Okay, I hope I've answered your question. Okay, so this is just an example of telecom. So here I did mention to you that where this big data adoption is coming in is that typically when you have erstwhile, people used to have traditional data warehouses, which is very, which is kind of, has a lot of constraints and also a lot of huge costs. Vendors like Teradata and things like that. They were all, and Oracle and others, data warehouse vendors. They used to make a huge profits out of their equipment and solutions, and people found that and they were not satisfying this with the needs of all this unstructured data and streaming data and all this. Your data warehouse and also very expensive solution. So that is where this Nortel is, as you know, is a telecom, one of the telecom providers in the North American region. They have actually proposed a big data based data warehouse, not the traditional data warehouse, where I already mentioned to you the powerful technique of schema on read and not schema on write. So you're able to dump, create what is called data lakes, and they're able to create this big data data lakes, and then you're able to store and process the data. And so what they found here is huge cost savings, because these Hadoop, the vanilla Hadoop systems are free of charge. Now, if you want vendor specific, you'll have to buy that. But typically, if you have the capability, you can actually build this cluster in-house. You can just download the Apache, Hadoop, and you can configure it. If you have the capability, IT and other capability, you can build it in-house. You don't need expensive vendors and consultants coming in and setting up your machine in your infrastructure. You can save a lot of money on that. So that's what this example basically illustrates. And obviously, data, CDR data and switch data and so many things happening. So for them, it is a classic case of where they implemented a big data solution to as a replacement for a conventional data warehouse. So this is like, I'm just saying, and some places they use a hybrid approach. They keep their ERP and all their warehouse systems, as well as maintain data, big data, and the very expensive kind of things, only they process it and push it in the data warehouse, where the vast majority of mundane operational tasks they use using big data and the Hadoop-based data warehouse. And where required, they're able to mix and marry these, different frameworks. So here is an example. I told you about predictive maintenance, right? I already have articulated, but I will just kind of come back to that once more. So you have different, you have reactive. That means once a failure happens, you do it. And then another is preventive, time-based. Like I say, every 6 months, every 3 months, you do it. Predictive is condition-based, based on the condition of the particular machine or artifact that you have. You can have preventive, predictive maintenance. So these are some of the factors. I think many of you already know it, so I'll not articulate. So unplanned breakdown, monitoring. So monitoring of equipment health is now you have the capabilities, all these algorithms and their systems available. You can have the capability of now monitoring equipment health. I gave you a fairly lengthy expose on the aircraft engineering, aircraft engine case study with General Electric. So these are all some things which are actually factors influencing equipment maintenance. So this is just a slide I got from one of the vendors, machine data. And so this is what, in case, just I thought it just for illustration. Now some of this I think was taken from Splunk, if I'm not mistaken, one of the tools available. So it allows you to log data. And if you see that data is not just a dumb data, as you see here, the data has a lot of these, what I call as mnemonics and identifiers. So if you see the data below, the sensor data, it has a date. If you see asset ID, the CV thing kind of thing is an asset ID identifier. Then you have a value here, and this is an alert. I talked about alert and alerts, right? So you have alerts, like you'd say, if you see below that, it says bad. If you see that particular line item of that log, it is saying that for that value is 50 and the quality is bad. So that's an alert. So maybe it may be some spinning device or some device, whatever. So if you're having some good insight, or you're basically monitoring your logs, you can actually have a lot of insights. If something is going wrong, you can actually looking at these logs, and if you have some utilities which can give you some good a way of querying the logs, you can actually have an alert. If you let's say some RPM, let's say in a T&D kind of electricity, let's say there is for whatever reason, due to some some kind of loading or actually etc., some capacity or light, some line feeder going off grid, and you have, let's say, some huge frequency variations. So if you're monitoring these kind of logs, there'll be logs there also, right? The generating station is generating logs, the turbine or whatever it is. You can actually analyze, and let's say you put that your tolerance, you cannot have more than, let's say, 1%. I'm just giving a very hypothetical example. 1% deviation from your 50 hertz. Assume. Okay. So the moment there is some device which is actually checking your frequencies, and if you notice that frequency is going to either 49 hertz or 51 hertz, it throws it out into the log saying that my frequency is starting to deviate. So if I'm doing this, I can immediately take corrective actions. Like maybe there's some line and maybe I can isolate that line and give an alter, or maybe bring some other things or take some corrective action. So that's what I wanted to illustrate using this kind of log. Then you have different levels, hierarchies, work order related logs, alarms and events. So different kinds of things logging data is actually generated. And this is an example, just as a diagram I'll show you. So you have a CNC drill machine, different sensors, APIs, application programming interfaces, lacks COTS. COTS, as you know, is commercial off-the-shelf systems. Maybe it's manufactured by a typical vendor and which is proprietary. In which case, only the vendor can give you you'll have to go to the vendor for each and every, query regarding any runtime data, whatever it is. And this is the final product, right? So just another example of machine data is like you have, just take one line item here. It is basically talking of the first thing is date, then a temperature sensor, timestamp, spindle sensor, chiller sensor, environment sensor. These are all probably some comma separated values. The headings give you the kind of what the data is all about, comma separated, date, time, spindle temperature, environment temperature, chiller temperature, etc. So that's how in this particular example, that's an example of machine data. And so these are some utilities in Splunk and others you have. You can have what is called as dashboards. where you can actually have, you can actually monitor the performance of your machine or whatever it is at your or shop floor or whatever it is. It shows a time, temperature. It talks about environment temperature, spindle temperature, chiller temperature, etc., right? It gives you in a dashboards. It can give you, so you can actually drill down and you can keep on querying a system to find out in a dynamic way. You can find out what's happening dynamically on the shop floor or in your factory floor, etc. So these are just some other examples, like drill machine usage, one-time usage. It gives you different graphs, different usage, plots, based on time and usage, and it gives you trend lines, time analysis, machine usage. Who is the user? You can do all these kind of things here by machine, which machine use, these kind of things that can be done. And this gives you a drill down into different. It's not very clear. I think when I copied it, it's not. So it gives you 3D scatter plots. Basically you can actually plot two variables against this thing and do some comparative analysis, statistical functions. You can correlate observations. Those of you have some exposure to statistics will know that one of the ways of visualizing data is using things called scatter plots, where you can actually plot data against a different axes and then do some comparative analysis. So here you have, in the bottom half, you have machine learning and also accuracy. That is, you have what is the predicted behavior and what is the actual behavior. You can do predictive analysis, and you can keep tweaking a model to make sure that your model is actually really accurate and is representative of the actual scenario. And so this is an example. If you remember 4 or 5 slides back, I showed you. If you use things like augmented reality, right? You can actually overlay on the basic machine. Now, typically in the modern shop floors nowadays, the foreman or whoever it is walking through, he probably doesn't have the time. There are, first of all, zillions of machines, complex machines. And then you cannot go into each one and query it and ask questions to your operator, etc. So nowadays you have links. You must have heard of Google Glass and HoloLens and all these things. Like there are different AR VR systems coming where you can have something like a head-up display. You can actually just, if your camera or something goes on a machine, immediately it pops up data, shows you just offhand. Quickly you can get a summary of the state of your machine or the shop floor or stuff like that. You can do now. The capabilities exist using things like AR VR. You can actually just different critical areas you do, it pops up and with all the summary data, and you can, at a glance, you can actually get good insights into the current state. And just to summarize here, what are the value proposition you can have? As I already mentioned to you, it is more flexible, cost is much less. The whole big data framework has come about, storage and processing frameworks come about because of the typical requirements of the kind of data generated, as well as from a cost perspective, right? So this is, you can use commodity hardware. It is fault tolerant. It is resilient. It has probably linear performance in the sense as the workload increases linearly, you can add capacity, and almost in a linear scale you have a trend line, as opposed to typically other equipment. It may not be linear. It'll probably be some exponential or whatever it is. That means if you add more capacity, more machines, or more processing power, you may not get linear performance. Whereas here in the big data frameworks, it almost guarantees linear. That is, let's assume that my computing requirement is going up in a linear on some particular form. I can actually plan my additional deployment of computing capabilities or storage capabilities in such a way that I can almost match it linearly. I think you understand, right? Let's say tomorrow, let's say I have a factory and I'm planning to add another machine. I already have, let's say, a data center which can process that. When I add the new machine or a new shop floor, I expect my computing needs are going to increase by so and so. So I am able to incrementally add computing and storage infrastructure in a way to optimally match the new requirement, as opposed to adding huge capacities for high costs in a one-time kind of effort. So it allows you incremental kind of addition of hardware, software, and storage to match your requirements. So as I mentioned here, linear cost increase. You can do small scale POC, especially startup companies. They heavily use this because they don't, when they start their operation, they probably don't have access to a lot of capital. So cloud and big data technology is something which really helps people a lot. using pay-per-use kind of models, and then you can have data storage. You can have humongous data storage with all these columnar database. You can have huge storage of data, and then you can have, as I already said, since you have this schema on read, so you can actually dump a lot of data. You don't need to throw away the data. So there will be a lot of valuable data sitting there in your, which is being thrown out, spitting out by your systems, which you don't need to, which erstwhile systems would have thrown out. But in your big data kind of framework, you can actually store it in your data lake and use a lazy approach to interpreting the data. And since the cost is low, you can afford that. If the cost is very high, you can't do that because it's constrained, right? You can't store low value data in a high expensive infrastructure. So this is just a summary of that. Say Industry 4 factory production costs are reduced significantly. And I was just reading a program, I think yesterday, day for in I think ET now or somewhere, where I was watching an expert saying that this logistic cost is a huge cost for manufacturing. Poor logistics can actually increase the cost very much. Supply chain related logistics inefficiencies, etc., can result in huge costs. So one of the key things in Industry 4 helps is also that since you're having this value chain also being able to, you're able to accommodate the value chain, your supply chain and your customers, etc., into the thing, into your overall, what do you call it here, your Industry 4, I would say, system. You're able to actually optimize you're able to adopt modern techniques and use the latest best practices for reducing costs. All your just-in-time, etc., was already the Kanban and just-in-time and lean manufacturing. But beyond that, you're able to use all the intelligence coming out with things like your IoT systems, your instrumentation, data, predictive and capabilities, your model capabilities. You're able to actually reduce cost a lot. And then plus, other thing, as I mentioned here, is that it is flexible systems. They're not very rigid. You're able to, your cyber physical systems or have the intelligence. They're able to have the autonomous and the capabilities and communication capabilities to, flexibly collaborate with systems and or human beings to achieve customization. And you can also have, even the production, as I said, the rigid fixed production system, flexible production system, but now we are talking about reconfigurable manufacturing systems. So both on the flexible customization part as well as on the production quantity part, you can have flexibility. So these are all some of the what do you call it, the benefits coming out of using of Industry 4 capabilities and smart factories. I think that's about it from my side. I hope you found it useful, and if you have any queries to ask, I would be quite happy to take those queries.
Thank you, sir. Thank you for a wonderful session. Now it is up to the audience. Any questions?
Sir?
Yes.
I have a question. So when we implement this big data for these industries, whether we can use the conventional internet or there is a need of dedicated lines customized for a particular industry?
Okay. That's a good question. So see, the public internet as we know it, see, if you see that thing, now it all depends on what you want to do. Now, if you're satisfied with the level of security and your performance which the public internet gives you, and of course nowadays you have all these providers like Jio and Air Bharti and all that, which give you a plan, like so many different plans available. So if that bandwidth and the capabilities, see, one of the key things for industries is cybersecurity and privacy, correct? So if you go for these normal plans, you have to actually rely on the cybersecurity and the data center capabilities of, let's say, a Jio or a Bharati team. And obviously, you'll sign contracts with them to say that let's assume you have very confidential, very important customer data being used here, where the order is coming from, who it is for, what kind of things. And it may be very confidential also. They may be producing some high-tech products, which you don't want the other opponent or some hackers and sitting in China to kind of hack and find out the data. So now it's not just the production is only one part of it. You have so many things related to data privacy, data security, obviously performance in terms of something. So it all depends. So if you are, let's say, defense manufacturer, you may want your, or let's say a vaccine manufacturer. Nowadays, the important debate going on is vaccine, right? We have Bharat Biotech, we have your AstraZeneca, and then you have your Pfizer, you have Moderna. So I'm told that when the vaccine research is going on, there a lot of hacking was going on, ostensibly from China and from Russia and all. People are trying to hack into your vaccine database to find out what the research is going on. So these are some other functionality you need to take care of. So now coming to your question, if you're a very small scale enterprise, you're just manufacturing, let's say, some commercial commodity hardware where your data privacy and thing is not very important, then your normal plans from some some internet providers will suffice. But let's say if you're in a high tech, let's say R&D establishment or some high tech defense or some high tech chip manufacturing or something like, where your data is a very high level of value and confidentiality, you may want some private solutions, like let's say private, let's say either your in-house what they call in-prem systems or private clouds using it, and lines with a high level of what do you call it, quality of service and contractual, both availability as well as privacy and availability, resilience. Was that clear? Was my answer, does it answer your question?
Okay, sir. Okay, sir. Thank you, sir.
So all I'm saying is that it depends on what is your industry. So per se, if you're just a normal supplier, I think these normal solutions, the public internet and your plans will suffice. But if you are doing some very, very high confidential work, you may prepare some private lines, MPLS lines and stuff like that, which is private, maybe a private cloud or in-prem, which is not accessible by the public or the public internet.
So another question from the audience is Ramya madam has given that how the frequency is recorded in the logbook.
Yeah, frequency. See, it all depends. Any variable you want to record, you need to have a sensor for that. Correct? Now it can be RPM sensor. If it's a speed, it'll be some RPM sensor. A frequency, there will be some frequency sensor. So one is you have a sensor which is capable of recording the data. There are zillions of sensors: temperature sensor, speed sensor, vibration sensor, acceleration, light sensor, gas sensors. There must be frequency sensors. There must be some frequency sensors. So the sensor, you have to identify a component, a manufacturer who's able to, in hertz, who's able to instrument it and capture it. And so one is that. Second is that the logs. So essentially, internal to the sensor, it will be some electrical signals or some signal, right? So essentially, that is actually has to be put out as a file. So maybe there will be some conversion process. So let's assume it is. Let's assume it's a rotary system, correct, which is turning, and you want to equivalently find the frequency 50 hertz. So that kind of, it's maybe an electrical signal. So from that electrical signal, you'll have to, let's say you want to, on the log, you have to record it as 50 hertz, 49 hertz. So that'll be a converter. So internally, it knows that it is 50 hertz, that frequency. It has to actually record it as a alphanumeric data in the log. So that sensor knows the value, correct? And it is able to, in the scale, it knows where it sits. 50 hertz, 51 hertz, 50 hertz. So in that physical phenomenon, which is the frequency, it has to translate that into an alphanumeric kind of thing, which says 50 hertz as a line item in a log file.
Good afternoon, sir.
Yes.
Actually, sir, myself, Ramya. Sir, actually, I'm working in RFID. So RFID data tags, I used to get millions of data because even though it was sitting in a position, I used to get millions of data. So I was doing a streaming data where I used a Spark to get the streaming data. So the issue which I felt was reading in the logbook, even the object was staying in a position, there were data was coming like huge. So from that, how to get the objects or the objects which are moving? Actually, I want the objects which were moving. So even the RFID, the object was staying in a position, the millions of data was coming, and I was collecting the streaming data through MQTT. So that was one of my questions, sir. How you are collecting this data, which is from the objects? And using the logbook, how frequent are you collecting the logbook details? Because there are like millions of data coming in like 1 minute.
Correct,
So
correct.
how frequently are you collecting it in the logbook?
Yeah, okay. See, that all depends. Let me first count to, first you talked about static and dynamic data, right? One is static data, one is data in motion. So there are different utilities, Flume, this, that's in the Hadoop ecosystem. There are other solutions which can actually capture data at rest as well as capture data in motion. So that's now second point I realize is a capacity issue. You're saying it is coming at a tide, it's coming at a huge, and are you able to what are the settings you need to put so that you're able to capture the data? Correct. If it is coming at a low speed of let's say 100, let's say 100 MB per minute, whereas let's say 100 terabytes per minute, you need to have different strategies. So what you probably need to do is that go to the settings. So when you configure your your system, you will have to tune it. You have to tune it in such a way that based on the way the data is generated, of course the system which you are using to store and stream inside also has a limitation. So first you'll have to mix and match. Excuse me. You'll have to mix and match based on your use case and the solution you're using. You'll have to mix and match. So let's say your RFID data is being recorded and let's say through POS terminals and is being streamed. So maybe you can use a queue approach. So rather than doing immediate capture and immediate sending, you can probably queue it into the queue you can configure. Let's say every POS machine or every machine, you say it should store or maybe every time based or based on volume based, saying that 100 items, if it shows, then one shot you upload. That is one tuning you can do. Second tuning, so that's one tune. Second is that you'll have to configure, find out your capability, sizing, based on the data speed and volume requirements. You'll have to tune your system to such that it's like an IO system, right? The source system is putting out data. Is the target system able to manage that the data is coming out at spitting out data? So you'll have to mix and match this thing so that the destination system which is actually capturing the data is able to capture it and be able to store it. So that's the essential problem. It's coming to a sizing and tuning issue. So you'll have to, and then coming to your point about how frequently you have to purge your data, store and purge it, that all depends on this thing. So depending on the volume of how much data has been generated at what velocity, what is your target storage system, okay? And then obviously if it's overwrite, see some logs are addend, keep on adding data. So in which case you don't lose it, it keeps on adding and adding to a upper limit. Now if it's an overwrite system, then you have to make sure that the data which is there earlier is not lost. So if it's overwrite, then you need to per se have to transfer. Whereas if it is an adding to the log file, you can keep on growing it to a certain extent. Is that clear? Did that make sense?
Yes, sir. Yes, sir. Actually, one more doubt is that sir, actually what you have said, I'm taking my data, I'm putting in a queue known as MQTT. So I'm queuing it. So since the data are coming like very frequent, so what I done is that after taking the queue, I plan for a hashing technique where I'll put the data into buckets so that using these buckets, my evaluation becomes easy, and then I can go for a prediction whether the object is being moved or not. So will that increase my computational speed? Because I am hoping for it to increase my computational speed, so I can do my prediction as fast as possible, because the data is coming very huge. So doing a hashing technique over the data which is coming from the MQTT, will it help me to come up with a more accurate thing?
No, hashing will probably help you in terms of access, correct? Access, it may improve the speeds, correct? Any other benefit you can think other than this? Hashing per se, it's more like a access kind of thing, right?
Sir, the main aim I felt was taking the data, then processing it like single thing you process, you put it into buckets and process it parallelly, it'll become more fast. So if I put the data which is coming from MQTT into 5 buckets, then the processing goes in parallel.
Okay, you're doing it parallelizing it. Yeah, but the one of the difficulties know, parallelization will probably increase the throughput. But the flip side is that linearity also has a structure, in the sense some data, let's say you want to do a cause and effect kind of thing. The data has to, let's say it's a time series data. So there is a sequence there. You cannot just parallel. I cannot take the first data, put it in one, second data in second. What will happen? You lose that time sequencing of it. So it depends on the, so coming to your question, it critically depends on the type of data you're doing. If these are independent data which don't have relationship between them, then your parallelizing probably should not have any, at least in terms of interpretation of knowledge, will not have much of, it depends on the log and what is it you're trying to do. If your analysis wants, let's say your analysis, let's say in a pause, you want to know how many customers are buying from this particular store, this product item. Okay. So, and you want to do some causal analysis. So if you probably split the data into multiple processing systems, that may probably not serve the purpose. There may be some other requirements where you parallelize will not really purely from a increasing a throughput and processing you want to do. So it needs to depend critically on the use case you're talking about. Make sure that you're in the process of optimizing or processing, you do not affect the outcome of the analysis you're looking at. That's all I would say.
Sir, if suppose I'm looking forward for a clustering, so that is what I'm looking forward. So clustering is my main output. So I want to cluster the streets, street areas where there is a water scarcity or something, like something just for a time I'm saying. So if it's so, clustering is my outcome. So based on my time, I am putting into buckets. So 5 seconds, 10 seconds, or maybe according to the distance, maybe 5 centimeter, like 5 kilometer radius, one bucket, 10 kilometer radius, one another bucket.
That's so, a cluster size. Okay.
Yeah.
Right.
So will I be able to, if suppose the GPS is my input, so GPS obviously will have the time frequency and the location. So if that is coming as an input in my MQTT, and if I put it into buckets where buckets are in the radius forms, the distance forms, will I be able to form my clusters at a very pace, like a fast pace, so that I can do a prediction or
See, I think as in any performance benchmarking, there is no one shoe fits all kind of thing. You will have to experiment with different settings. Like all these benchmarking, like when you say you want throughput and all, you will have to try out different loads, maybe at different intervals, configuration settings you try out. And it will also depend on the use case. So what, maybe there is no one answer. What I would request you to do is that for different bucket sizes, as you call it, maybe radius, lat long, different this thing, you just tweak it and run multiple runs and do a test exercise, and then maybe plot some graph, and you're able to find out some insights based on the type of data that you have. You will see where the maximum throughput is obtained for that particular problem set and use case you're doing. So maybe you can do this as simple simulation for multiple settings of different bucket sizes and or lat long settings. Maybe have a few things, see and calculate the IO and processing for teraflops or whatever you call it there, plot a graph, and then because based on the data, only then you'll be able to tell. You cannot, maybe there is some setting in between which gives you the best output. It may not be neither the extremes, it may be some value in between. So you can actually do an experimentation on that and then arrive at the best solution. And that may change from use case to use case. It may not be the same setting, may not, for if you have, let's say, a different problem you're doing, that setting may not work. So you'll have to do some kind of a tuning, performance tuning, to arrive at the best parameters selection.
Oh, okay, sir. Actually, that I had that doubt because I want to know whether like MQTT alone will do, or hashing or bucketing may help this do better. So I had whether will this bucketing help or not. That was my actual doubt. And sir, actually, you cleared like my most of my doubts. Thank you so much.
Thank you.
So thank you, sir. Thank you, Ramya madam, for making us an interactive session. So let me invite Abim for the vote of thanks.
Good afternoon, everyone. So for the almost last 2 hours, we had a section on data analytics for Industry 4.0 by Dr. Venugopal sir. During this section, he has covered what is Industry 4.0, what are different elements of Industry 4.0, what is the importance of data analytics in Industry 4.0 with some very good examples. So on behalf of our entire Mechanical Engineering Department of Vishwajyoti College of Engineering and Technology, I thank you, Venugopal sir, for spending your valuable time with us. Also, I thank each and everyone present here for attending this section. And thank you all. We'll see you in the afternoon with another section. Thank you all.
Thank you, sir. Once again, thank you for accepting our invitation and delivering a very good lecture and informative one. Thank you, sir.
Thank you.
Participants, we winding up the session 2, and the session 3 will start at 2 p.m. Thank you.